If you've ever felt completely overwhelmed by advanced abstract algebra, you are absolutely in the right place today. We're going to take these big, intimidating concepts and break them down using super clear, relatable analogies. I am so incredibly enthusiastic about this topic, because honestly, once you see the hidden machinery behind mathematics, it completely changes how you view the entire subject. So, let's get ready to unlock the secrets of sets, binary operations, and proofs.
Here's our roadmap for today. First, entering abstract algebra. Then, the rules of binary operations, finding identity and inverses, visualizing with Cayley tables, solving advanced algebra problems, and finally, revealing some elite exam proofs.
Section 1. Entering abstract algebra. Okay, let's dive right into this with a major paradigm shift.
To really get what we're doing here, we've got to compare where you've been with where we're going. Elementary algebra? That's what we all know. It deals with regular numbers and fixed operations. 3 plus 5 equals 8. It's highly specific. It's kind of like driving a specific car, right? Let's say a Honda Civic. But abstract algebra? That shifts the whole perspective. We aren't just driving the car anymore. We're popping the hood and studying the overarching concept of the engine itself. We're looking at the fundamental behavior and structural properties of operations on totally generic elements.
And in this totally new abstract world, we honestly do not care what the elements actually are. They could be numbers, sure, but they could also be matrices, functions, or even crazy geometric symmetries. We are making a massive leap from just doing basic arithmetic to studying true algebraic structures. Literally, the only thing that matters now is how these elements combine.
Section 2. Rules of binary operations. Because, hey, every good game needs strict rules, right?
So, the whole game of abstract algebra is governed by the rigorous definition of a binary operation, usually denoted by an asterisk. A binary operation on a non-empty set S is a function that assigns to each ordered pair of elements in S exactly one element in S. Put simply, you just grab two items from a specific group, combine them using some rule, and boom, you get exactly one single result.
But wait, there is a massive catch here. It's what's known as the golden condition, otherwise known as closure. For that asterisk to be a valid binary operation, the output of A combined with B must absolutely always belong to the original set S. If even a single pair spits out a result outside the set, the whole operation is broken. It is not binary anymore.
To make this totally crystal clear, think of closure like a super exclusive VIP club. If two members of this club interact with each other inside the club, the result of their interaction absolutely must be another member of the club. No outsiders allowed, ever. If their interaction somehow creates someone who isn't on the guest list, the club totally loses its VIP status. And that, my friends, is mathematical closure.
Now, people often mix up closure with another concept called being well-defined. Let's clear that up right now. If closure is the VIP club keeping outsiders out, being well-defined is just like a person changing their outfits. If you wear a sharp suit one day and sweatpants the next, you look totally different, but you are literally the exact same person underneath. In math, if we change how an element looks, like writing 1/2 instead of 2/4, the underlying mathematical reality of the operation cannot change. The result has to be exactly the same.
Section 3. Finding identity and inverses. With our VIP rules locked in, let's meet the two VIPs of these algebraic systems, the identity and the inverse.
First up, the identity element. The formal definition goes like this. Let the asterisk be a binary operation on a set S. An element E in S is called an identity element if, for all A in the set, A combined with E equals E combined with A, which just equals A. And there's a really powerful theorem here. If an identity element actually exists in a set, it is completely unique. There is only one.
But what does that actually mean in plain English? Think of the identity element as the mathematical mirror. No matter who stands in front of this mirror, they just see themselves perfectly reflected back. Say the element is 5 and the operation is addition. The mirror is 0, right? Because 5 plus 0 is just 5. The mirror changes absolutely nothing.
And once we find that mirror, we can track down the inverse. For each element A in the set, an element A' is an inverse if A combined with A' equals A' combined with A, which leaves us with E, our identity element. Notice that? The whole definition of the inverse relies entirely on finding that identity element first.
So if the identity is the mirror, the inverse is basically the ultimate undo button.
Imagine you're typing on your computer, you make a mistake, and you hit Ctrl-Z to undo it. You are right back to that blank, neutral page. In algebra, combining an element with its inverse instantly neutralizes it. It brings you right back to that mathematical mirror state E.
Section 4. Visualizing with Cayley tables. Okay, we get the abstract rules, but how do we actually visualize them?
Enter the Cayley table. Whenever we're dealing with a finite set, meaning a set with a specific limited number of elements like E, A, and B, we can map out the entire binary operation using a matrix-like grid. You just read it by taking an element from the left column, combining it with an element from the top row, and boom, your result is right there in the intersecting cell.
What's genuinely amazing about this is that we can literally spot our algebraic properties just by glancing at the layout of this grid. Step 1. Checking for closure. Are all the outputs inside the grid part of our VIP club? Yep, we only see E, A, and B. 0 outsiders. Step 2. Commutativity. If you draw a diagonal line from top left to bottom right, is the table a perfect reflection of itself? If yes, then A combined with B equals B combined with A. And step 3. Finding that identity mirror. Just look for the row that perfectly matches the top header. Notice how the row for E matches the header perfectly? That confirms E is our mirror.
Section 5. Solving advanced algebra problems. Now that we have the building blocks and visual tools, it is time to graduate to the real deal. Let's apply what we've learned to solve some comprehensive algebra problems. Think about this challenge for a second. We're given a totally custom binary operation. A combined with B equals A plus B plus A times B. In this wild new system, how on earth do we find our mathematical mirror, E, and our undo button, A prime?
Well, we just systematically follow our rules. To find the identity, we set up the equation A combined with E must equal A. Using our custom rule, that becomes A plus E plus A times E equals A. Subtract A from both sides, factor out the E, and we get E times the quantity 1 plus A equals 0. So our mirror, E, is simply 0. Now for the inverse. We know A combined with A prime must equal our mirror, which we just found out is 0. So A plus A prime plus A times A prime equals 0. Move A to the other side, factor out A prime, and divide. Our undo button, A prime, equals negative A divided by the quantity 1 plus A. It is honestly so satisfying when the algebra just falls perfectly into place like that.
But definitely beware, because not every custom rule plays nicely. Take this specific example. If our rule is A combined with B equals 1 plus A times B, it utterly fails the associativity test. If you group A and B first, then combine with C, you get a totally different algebraic result than if you grouped B and C first. And when fundamental properties fail, the whole structure just collapses.
Section 6. Elite Exam Proofs Revealed. We've officially arrived at our final destination for this explainer.
You've mastered the rules, you found the mirrors, you hit the undo buttons. Now let's tackle an elite mathematical proof. This is a classic, beautiful proof showing that inverses are unique. Basically, we want to prove an element can only have exactly one undo button. How do we do it? We play a little logic game. We start by pretending that element A actually has two inverses. Let's call them B and C. Now, watch the logic unfold. Let's look at the expression B combined with A, all combined with C. Because B is an inverse of A, B combined with A turns into the mirror E, and E combined with C is just C. Okay, now let's group the exact same elements differently. B combined with the group A combined with C. Because C is also an inverse of A combined with C becomes E, and B combined with E is just B. Because valid binary operations must be associative, grouping doesn't matter at all. Therefore, the result of the first calculation, C, absolutely must equal the result of the second calculation, B. We just logically forced B and C to be the exact same element. The undo button is proven, without a doubt, to be uniquely one of a kind.
And that brings us to the end of our journey into abstract algebra. By stripping away the specific numbers, we basically discovered the invisible skeleton of mathematics, the VIP clubs, the mirrors, and the undo buttons that make everything work. So I'll leave you with this provocative thought. If concepts like identity and inverses are always perfectly unique and structured in these abstract mathematical systems, what other flawless hidden structures are secretly governing the physical universe around us right now, just waiting for us to figure out the rules? Keep exploring, and I'll catch you in the next explainer.